studying nuclear materials engineering, and specifically my project is on the radiation creep fatigue of F91 and A709 stainless steels. And I will get into more of those definitions as we go. But I always like to start my presentations with a little overview. So first, I'm going to start with an introduction into my research. So I'm going to answer what are the real world applications of F91 and F709. Again, those aren't just a random collection of letters and numbers. They actually mean something in the world of steel. So I'll get you guys caught up on that. And then what exactly do I mean when I say radiation creep fatigue? Well, those aren't just made up words. They have meaning to them. So I'll define those for you guys so you have a better understanding of what exactly I'm looking at. And then why exactly do we care about radiation creep fatigue? And why is it something worthwhile to research? And then continuing on, I will talk about my experimental setup, what equipment I use, how a radiation creep fatigue experiment looks like, what things I'm looking for, how do I process data and present data afterwards. And then finally, I'll go into some preliminary results I've collected thus far and any future work that I may need to do down the road in order to get the experiment set up better or just more work in relation to my thesis down the road. So starting with, I want to talk about the applications of F91 and A709 stainless steel. So in the world of nuclear, stainless steel is king. So pretty much anything you see in a reactor that makes up like structural components of reactors is made of some grade of stainless steel. So one very common grade is 316 stainless steel. So if you think of things like kitchen knives or like old kitchenware, stuff like that, a lot of that is made from 316 stainless steel. And some of that is also used in reactors. And so things like the pressure vessel, where that is where the water is being boiled by the fissile material, which then turns the steam generator, which creates the electrical energy. That's that huge structure, which you see in this middle picture here, is made of stainless steel. Coolant tubes, which brings in cold water to cycle out and condense the steam once it's gone through the turbine, is made of stainless steel, and then something called baffle bolts, which I'll get into later or in a little bit, make up another component, big component. So why are we looking at grade 91 and A79? Because these materials are in very extreme environments. So I like this quote here. I actually don't know who originally said this quote, but I think it's very good in in just saying what exactly is it. So proposed reactor concepts require new materials that can perform in coupled extremes. But what I mean by coupled extremes is high temperature, high mechanical stress, and radiation. And so those things combined can do something like this. So this is what I was talking about. So this is a baffle bolt, and that holds parts of the pressure vessel together. And if stuff like this cracking forms, that's not good. We want nuclear to be good in the public eye, and if things like this happen, people will stop liking nuclear, which is not a good thing. So we want to look at different materials that can not do this. We want to prevent this from happening ever. So this is why we're looking at grade 91 and A79 as possible materials to replace structural components in reactors to make them longer lasting and safer. So now we can go on what is radiation creep fatigue. So I'm going to break down piece by piece. So we're going to start with radiation. So radiation, simple definition, the act of applying radiation to a material causing microstructural damage. So I like to think of it as you've got the world's smallest bullet that being a subatomic particle, whether it be a neutron or a proton, and you are shooting it at the world's smallest target, which is an atom within the lattice of a material. So essentially what's happening in a reactor is all these neutrons are whizzing all around. And those strike atoms in your lattice of structural materials. What happens? So those atoms can get knocked out of their lattice and create defects, which then cause different things to your material, things that we don't want, like you saw the cracking before. So that's sort of what we're looking at with the radiation. Next, what is creep? So creep is the deformation of material under high temperature when a force is applied. So what that means is materials like to deform when stress is applied. So think of like you played with Play-Doh before, you've like pulled it apart and it like stretches out and then like starts to break. Think of that, but over long time periods and when a high temperature is applied to your material. So that's kind of what's happening over time in a nuclear reactor. And so we want alloys that resist that, essentially. And then finally, fatigue. So fatigue is exactly what we think it is. So in material science terms, fatigue is deformation of the material from the result of external stress being applied in cyclic manner. So think of it as like stretching out, relaxing, stretching out again, relaxing, and over again. Because in a nuclear reactor, you're not running all the time 24/7. You have times where you're shut down, and you're kind of like letting things settle, and then you're ramping back up again to produce energy, and then you're shutting back down again. So there's that fatigue part in it because you're going up to high temperature, going back down to room temperature over and over again. So that fatigue wears down the material over time. And then all those things combined is what I'm trying to look at to see if all three things conflict with each other, make things even worse, or do something to cancel each other out. So we're trying to see what exactly happens. And so now I'm going to move on to my sort of more hard research, hands-on stuff. So I am working with Oak Ridge National Lab and the University of New Mexico and University of Tennessee Knoxville. And part of this project is we received material from Oak Ridge National. And so on the left here we have the bulk grade 91 stainless steel. And I would have, so these white boxes here, I would have the elemental composition. So that's basically just saying what's the recipe of elements that make up this material. Unfortunately, the scientist at Oak Ridge was not able to get it to me in time. So that'll be something in the future that I can show you guys if you'd like. So I got a rod of F91 stainless steel, and on the right, the A709 stainless steel is a block. And you'll notice on the block, there's an arrow and the letters RD. So that means it's the roll direction. So when you're making this blocking material, part of the process is what's called fold working. So that's basically you have these two giant wheels that you're like pushing your metal through, and it's like rolling it, and it's like working the microstructure of the material. And so that roll direction will come into play later. I'll show you guys. So moving on, we're going to move on to the specimen. So this right here is the specimen geometry of like how we test samples, like what the end product of samples from that bulk material that we're going to be testing. And so these follow standards within material science. And so I'll kind of break down the schematic and kind of like for you guys to understand what's going on. So first we have this part called the end cap. And this is where the load is being applied. So you see that large fillet kind of on either side of that. That is where the load is applied, and that's with something called shoulder. And there will be a picture of a loaded sample that will kind of make that clear, but just wanted to throw out that definition now. And then the two holes, the top one is for a thermocouple, so that is a piece of wire that essentially reads the temperature of the sample. So that's how we know what temperature the sample is at when we do an experiment. And then the bigger sample is so that way there's a screw that pops up, and then that way it sandwiches with the grips. And I'll get more into that when I show you the machine that we use to pull apart these samples. And then this middle region here is called the gauge region. And this is where the focus area is. This is where we target the irradiation, so that's where we're shooting our little bullets of ions at the target. And then this is also what determines the stress. So stress is force times cross-sectional area. So we can change the stress depending on the geometry of this part. So for instance, this part has a gauge region with a width of 3 millimeters and a thickness of 2 millimeters. So we have 6 millimeters across, 6 millimeters squared cross-sectional area. And then that is essentially being pulled. And so that's what determines the stress, because we then apply a force, and we force times cross-sectional area is stress. And that's what I'm talking about with the varying geometries, because part of our experiment is when we have these straight side samples, we can only do one stress state, but then we're also looking to, okay, what if we have, instead of parallel lines for the gauge region, what if we have them more triangular, so it looks like a trapezoid? Then we have a stress gradient. That's more for future stuff, but this is just kind of to get you guys familiar of what exactly the samples look like. And then here is part of the experiment setup. So this is in what we call the Alpha Lab, and this is the NewTek exosome chamber, and then the MT1000, which is a micro-mechanical tensile tester. And so we purchased this recently from a company called NewTek in France, and it is with, let's see, I think it was last week. It is now finally up and running. We are just waiting on getting a computer to control everything. So I'm just going to walk through and kind of explain all the different parts to you guys. So first, we have this computer here with software called SoftString and VAC6. So SoftString controls the microtensile machine, and then VAC6 controls the vacuum chamber itself. So we have these two pieces of software that communicate with the device that we use to conduct our tests. Next, we have the control box, and this is kind of the middleman between the microtensile machine and the computer. All the computer commands go through the control box, which then controls the microtensile machine. And it also provides cooling and all of that. Next, we have the exosome vacuum chamber. So we put this in a vacuum chamber because when you heat up a piece of metal at high temperatures, if it's left in atmosphere, it likes to oxidize. So essentially, it likes to rust. And we don't want that happening. We want to purely look at what's happening to the metal. So we have it in a vacuum chamber, so that when we heat it up to temperature, it doesn't rust. And then we have the speakers. So on the left, the gray thick cables are the heating and electrical cables. And on the right, those two clear tubes, that's for cooling. So cold water goes in, hot water goes out. And then finally, under the desk, we have a roughing and turbomolecular pump. So those are to pump down the chamber, down the vacuum. So this chamber goes from atmosphere, which we like to use units of 4. I don't know if you guys are familiar with 4, but atmosphere is 750 torr, and then we like to go down to a vacuum of roughly 1 times 10 to the minus 5. So very very low. Well, not super low, but like a decently low vacuum. So to mitigate that oxidation when we heat up our samples. And then finally, inside the chamber itself is the M1000, MT1000 microcrystal. And so this is what I was talking about before with the sample geometry. You can see on the rightmost image those four ceramic blocks, those little pan ceramic blocks. Those interface with that fillet where um, that's where the force is like being applied. That's where like the sample is being pulled in, as you can see. Next up, we have the Michigan Ion Beam Lab. So this is where the magic happens. So this is where the radiation. Uh, so this is a nice, lovely picture of the entire lab. It is actually the only ion beam lab with, or only university ion beam lab with three different accelerators. So it uses the power of accelerators, particle accelerators, to simulate radiation damage that we would find in nuclear reactors. So the thing about nuclear reactors is the radiation damage is super. So we determine every damage by radiation in units of EPA or displacements per atom. And I will go too in depth there. That's a lot of stuff right there. But essentially, when we use an ion beam accelerator, we can simulate damage from a lifetime of nuclear reactors, so like 40 plus years, in the span of 10 days. So we can see end of lifetime material deformation in like a fraction of the time we would see in a nuclear reactor. So this is super important for classifying which materials are safe to use in a nuclear reactor. So let's sort of explain. So we'll kind of go on the journey of a single particle as it's going through this setup. So this red dot here, you see, this is the source. So this is where either, like for example, in our experience, we use protons. So we have a canister of hydrogen gas that's here. And then that hydrogen gas goes through some fancy technology stuff. I will get too into it. Essentially, it ionizes. So we rip apart the electron that was on the hydrogen, and now we're left with the proton. And now that proton is being coaxed down the line into the accelerator. So that's that big tube that you see in the middle there. And then it gets sped up. So it accelerates. Essentially, there's some large magnets that propel it along up to 3 mega electron volts, which is in particle physics terms decently high energy, pretty fast. And then you can see it reaches this fork in the road. And so then we use bending magnets to steer this beam down whichever beam line we line up. So that is actually what we're talking about. So beam line 1 is where we do our experiments. And so it goes down that beam line down to the target chamber, which will then hit this sample. So this is a picture of the current group setup. All the stuff that I showed you previously is essentially Gen 2. There is a PhD student senior to me who is also doing group stuff, but she's doing it all on this old setup. And it's kind of this out with the old, in with the new situation where I am taking over and building up a new creep setup for this stuff. But still using similar methods to before. And then finally, what do we do with the materials after we irradiate them? So how do we kind of extract meaningful data? And that is with microscopy. So essentially, we material scientists we pull biology and we look at it under a microscope. But instead of this microscope being optical, it is electrical. And so we use something that looks like this. And this is a Toscan Mercury FPG SM. So what is that? So that's just the company's fancy name for this thing, and it is an electron microscope. So the SEM stands for Scanning Electron Microscope. And so an electron microscope shoots electrons at whatever you're trying to look at, and essentially gives you a high resolution image of what you're looking at. And it has magnification all the way down to nanometers, so 10 to the minus 9 meters. Very, very small. And so you can get cool things like really high resolution images of your sample. And you can also get things like this very colorful picture in the top left of the middle image, which is something called electron backscattering detection, which gives you this colorful map, which essentially shows you the grain structure of the material. So the grain structure is this different crystal orientations, which I can get into more in depth if you guys would like later. On the other hand, we can go even further with a TDM. So a TDM is, instead of scanning electron microscope, where it basically has a beam of electrons that scans across your sample to give more like surface stuff. TM is transition electron microscope, which means that instead the electron beam goes through. And in order for that to happen, you have to take out a lithotripsy, which is a like super tiny, thin slice of your material. That's like nanometers, so extremely tiny. But that way, the electrons can go straight through, and then you can even see like on very powerful ones that I will never be able to use. But very powerful TMs, you can see individual atoms. But the ones I will be using, you can mostly just see bulk structure names. But yeah, so that's kind of how we look at materials and see what's going on inside. So now we kind of go on to some preliminary results. So this was part of learning how to use the MP1000. So that was like 2 or 3 weeks ago. The CEO of the company flew off from France and he taught us how to use the machine. It was really cool. So we just did a simple pencil test. So we pulled the material and fill it essentially. As you can see, the sample is broken in the middle there. And you see this discoloration because of temperature. When steel is heated up to a temperature, it gets this discoloration. And then it generates a stress strain curve. So strain is how much your sample has elongated, how much it's deformed from its original dimensions. And that's expressed in a percent. And then we have the stress, which I was talking about earlier, how it's the force times the cross-sectional area. So what a stress strain curve tells you is how strong is the material? What sort of stresses can your material take before it breaks? So that's kind of what I'm kind of showing here is it's going up, and then it's kind of like slowing down, and then finally it just breaks and just dives. And so that big dive is where it breaks and it's no longer able to take any more stress. And then we're also doing a cool experiment where we actually put the micropencil tester in the SEM, so that image before from the last slide, we actually put it in the microscope. And that way, you can take these maps here, which show the grain structure, and then you can pull apart your material and see the grains elongate over time. But in this experiment, we really didn't pull it enough to actually see that, but I mean, we learned how to take an EBSD now, so it was cool. And then next is for some future work. So I showed you that bulk material. How am I going to make samples? So I need to figure out a plan to do that. So I kind of figured out this 3-step process that I still need to actually test and see if I can actually make samples. So I've modeled up in SolidWorks the bulk material that was given to us, and I was like, okay, so how am I going to do this? So one thing I thought was like, okay, we like CNC milling. That's a really easy and surefire way to cut out metal and everything. So what if we use a CNC to essentially mill out an extrusion of that profile of the sample? And so what I was talking about earlier with the roll direction and everything, that's important because you want the gauge length to be along that roll direction because your grains are aligned on that roll direction. So we want to look at the grains in that orientation with your sample. So that's why I have the samples oriented the way they are on the pork potato. And from there, we pursue something called wire EDM. So wire EDM is electron discharge machining. So it's basically just think of a bandsaw. You know how a bandsaw like is like revolving and then like you just press the material and get cut through it. So essentially that instead of a saw like a flat saw blade, you have just a wire. Now wire is charged up with some current and then you are able to essentially zap material away as you're going along. And so then it allows us to essentially create this path here where you just keep going. And I like to call these bread slices because you have this loaf of bread essentially that is the sample profile, and now you're just making slices out of it. And then you can set whatever thickness you want your sample to be, and you just chop it up. And then from there, in order to actually get it ready for an experiment, is electric polishing. So electric polishing is just a really fancy method of sanding a material. So electric polishing is a chemical way to do so. So you have this electrolyte, and then you put your sample on the positive end, connected to a power source, and then you have a anode or a negative end. And then you dip that in there, and then you turn on the power supply, and then essentially individual atoms are being ripped off your sample, and you get a really nice, shiny, smooth. And you really want that for your reactions. And so that would be the final step, kind of clean up your sample and get it nice. And then finally, I was talking about how we have a crib set up already, but it's kind of like outfield engineering. So we have to design a new vacuum chamber in order to hold the microphone cell test. So that's another thing that I've been working on is I've been developing this um, vacuum chamber, which has all these different ports. We like to call it. It kind of looks like one of those old steam mines. It's kind of like ridiculous with all its different ports and everything. Um, why do we need all these ports? So essentially, we need to account for first. Well, it needs to attach to the beam line, of course. So we need it to be able to actually receive the beam. So there's one port for that. We have a high definition camera. So the camera is used to make sure the beam is aligned with our sample and everything is on target, essentially. Uh, we need to actually see what's going on inside, so we need lights. So we're going to put lights on there. And then we also need to have a way to measure temperature. So we have something called what's called a FLIR. So essentially, it's a thermal camera that looks in, and due to uh, uh, um, uh, so this certain emission coming from the sample. I can, the word is escaping me, but essentially it reads the temperature of the sample without having to physically interact with it. And finally, we need these cameras for what's called stereo DIC. So DIC stands for digital image correlation. So essentially, these cameras take pictures, like a ton of pictures at a time. And what these pictures do is you can put it into software and you can see the gradual change in dimensions of your sample. So it's a way of tracking that strain that I was talking about earlier. The machine itself does it intrinsically, just by how the crossheads are moving away from each other. It's measuring that over time. But this is just another way to do so, just to verify that our measurements are correct. materials. We always measure twice, cut once, as the saying goes. And so finally, in conclusion, we first, in the presentation, kind of walk through, okay, so why, as a material scientist, are we looking at these materials specifically? What are they used for? What are we trying to avoid? Then we kind of moved on, okay, so what is my experience setup? How do these materials look, what do these materials look like? And what capabilities do I have experiment? And finally, what is some results that I've done so far? So I've been able to get a system to learn how to use the machine. And then there's some future work that I have to do is actually get a sample fabrication plan together and have like a pipeline from bulk material to sample, and then actually setting up a vacuum chamber and full experimental setup on Beamline in the Michigan Lab. With that, thank you all for listening to my presentation. Any questions?
Yeah, so I was wondering, how much have you looked at it underneath just like a regular SEM? Like, does it have like pre-printed fatigue lines and stuff?
Not much at all. That was just based that system. So uh, wait. So that was just essentially to learn how to use the MP1000 within the SEM because it has essentially has software set up. The SoftStream software allows you to set up an experience so that you can literally just type in what you need, walk away, return the next day, and your experiment will be done. So it was just more of a learning experience on how to use the pencil tester in the next year. But in the future, we will definitely be looking at creep and fatigue lines changes.
So you kind of focus on steel and stuff like that.
Mm-hmm.
Is there like other materials that people have been kind of interested in as well for
Oh yeah,
advanced?
there's loads. So steel is kind of the main thing because people like picking up construction materials, but there are other things in the reactors. So like there's things called there's like cladding material or moderators. Moderators usually are made up of ceramics. So one of my friends in a different lab, he's working with beryllium carbide as a moderator. So he's looking more at ceramics or yeah, that's kind of the two, or another guy in my research group who's looking at hydrides, which is kind of another kind of down the road of ceramics, that sort of thing. So yeah, there's looking at steels for, um, but more, but for sure the more popular thing is like iron carbon uh, based alloys. Otherwise, like nickel alloys are really popular because for stuff like molten salt reactors, which deal a lot with corrosion, you want something that is corrosion resistant with nickel. So,
If no one, anyone else have another question?
I was just gonna say like some other factors that might be important to like the material, like why steel is important. So like is reflectivity a big thing because you're micro polishing it, and then also like the coefficient of expansion contraction.
mhm. Are you talking about thermal expansion? Is that kind of what you're getting at?
Yeah.
Yeah, so if you'll notice in the system there, you kind of got that saw blade towards the top, and that is due to thermal expansion. So essentially, you set the rate of how fast you're pulling the material apart, and if that is similar to like how it thermally expands, then it's the machine's not going to know what to do essentially. So it's like just like confused as like, oh, the sample is stretching due to thermal expansion, but I need to account for it. So it's like pulling more, and then it's like, oh, pull too much, and like so that we have like considered that, taking that into account. And then for the reflectivity thing, um, so that is why we do the electropolishing, just to have that smooth surface, because our beam is normal to the surface of the sample. So that is essentially um, kind of mitigating that reflectivity. And if there is some reflectivity, then that's it's not that big of an issue because it damages damage essentially. So we're just looking at like how the radiation interacts.
If no one else has a question, I'm gonna go again, but I'll let everyone else sit here and ask a question if they have it. Going once. Going twice. All right. So obviously there are probably other ways that this could fail other than creep fatigue. So do you know of any other competing things, and like how does creep fatigue, I guess, rank in terms of the most common means of failure compared to those?
Yeah. So there's a whole slew of ways it can fail. So I wish I had this presentation. That's actually a good thing. So there are four things that even material scientists like to look at when there's failure. So corrosion, mechanical stress, thermal stress, and radiation. So we have this sort of Venn diagram where we look at different couplings of those four and all the different permutations. So yes, there are a lot, and I can't name them all off the top of my head. But so like Mackenzie, the PhD student who's senior to me, she's looking solely at irradiation. So what I'm doing, but without the fatigue. So I'm just adding the extra fatigue, and that has its own sort of stuff. And so I don't know where that ranks with irradiation fatigue itself. It may just be like we're looking at two different time scales essentially, where I may be looking at longer time scale because fatigue is over cycles, so we're looking at long periods of time. Whereas Mackenzie's more looking shorter because it's just radiation creep. Or there's irradiation-assisted stress corrosion cracking, which is a more mouthful, but essentially it's just like a whole, like I think that's the one that's all four of them together, and that's just your materials just getting blasted with everything. So it of course just gets destroyed. So it really depends on what kind of reactor you're designing. That depends on what sort of degradation types you are going to be facing. And then I don't have a surefire answer on like what the rankings are in terms of what makes something fail. Because it also can depend on the material, and that's kind of why we're doing all this research, is to essentially look at, okay, like how do these things, what causes these things to fail, and how fast and how violent, and how can we stop it essentially. Hope that makes
Just to kind of piggy off that as like a materials engineering undergrad major, it was a whole semester long class for failure analysis.
sense. Yeah, failure analysis. There's a lot, which is why simulation is so big, because you can just tell a computer to run equations and then you get it. And I've actually tried to use a program called ANSYS to kind of run some very basic simulations on that sort of stuff. It's only just to like see how like temperature moves through a sample and everything. So eventually, I think it'd be kind of cool to try and like get it to do full scale simulation of the whole see what happens before I even.
This is just kind of loosely related, but like, how big of a thing is 3D modeling, like between you and your peers? Because like undergrad, it wasn't like required to graduate, and so it's kind of interesting the field research that you're doing it.
Yeah, I would consider it more like one of my tools in my toolbox. So it's great for kind of designing and drafting and kind of figuring out, okay, like how, like for sample design, like that's, well, it's very useful for sample design because we can do this rapid prototyping and be like, okay, like here's an idea here, and then we go into the meeting and then my professor's like, that's a stupid idea. I'm like, okay, and then come back next week and lift it, and he's like, okay, getting better, that sort of thing. So I would say it's a nice tool to have in my toolbox. That's the way I think
Tony, I know you're a forestry background guy. Uh, you got any weird questions for Wyatt based off of that?
Um, actually, I just an observation. I feel like you did a really good job explaining that. That was never. I have a pretty good science background, so everything you explained pretty much made sense, which I was surprised about.
That's awesome. I'm glad to hear it. I think that was my one goal that I had. Was like, I want to make sure that people understand. Because I find it too often in science, everybody likes to sound as smart as they possibly can. So they throw out the big words, and they don't understand what just get everybody to understand what you're trying to do.
Yeah, no, I think you definitely should do that.
Thank you. Thank you.
Well, I planned for like 3 more minutes. If we don't have any more questions, I have one that I think. Well, actually, I'll split it into two. So, one, what would be like the holy grail for your research field? You can answer this one last. And then two, with respect to this beamline method of trying to speed up basically what a normal reactor would experience in like 40 years, are there limitations to that method? Like, are there certain artifacts that you're more likely to see?
I can't give you a direct answer to it. I'm going to sort of I can't give you a direct answer. That's funny because there's a research project that my roommate is working on. He's essentially comparing data from reactors that are like in operation right now. They essentially just threw a chunk of material close to the reactor, took it out, and now after a long time, looking at it, and he's comparing it, trying to essentially simulate the same environment with the ion beam, and seeing like, okay, do these compare? Do these give the same results? So essentially verifying if what we're doing is actually um, correct and accurate. But for the time being, it's just what we do for now because it's quick and it takes forever to validate materials to be used in the reactor just because it's just a bureaucratic nightmare. It's just a lot of paperwork and all that stuff. So, but off the top of my head, I think I think they are pretty comparable from what I've kind of seen from other people's research. I think the microstructural damage that you see between the two are similar, uh, and there's just been enough research done that it works out. So I know that's not a super satisfying answer. I'm not quite satisfied with how but there is work being done to make sure that this stuff is actually accurate. And as for the holy grail of my research, I wouldn't say there's like a certain material that we're searching for, essentially, just because that's like that's essentially like going. You go insane before you find the perfect. Um, so we're just trying. We're more looking at how these three things, the radiation, frequency, how do they affect the material? So we're using that knowledge to then better inform metallurgists to choose elements to alloys and materials to kind of mitigate those things. So we're kind of looking more at the um, more of the sort of like mechanics of what's going on, like kind of like looking more at like, okay, what's the physics behind it? How can we explain what we see? Um, that sort of thing. So I don't foresee us finding a material that's just like insanely resistant to all of this stuff. Maybe in the far future when we're all materials wizards and our technology is so far advanced that we have nothing to worry about. But for the time being, I would say we're just trying to accrue knowledge, essentially. So I would say the holy grail would be uh, methods of obtaining um, uh, knowledge faster because creep experiments take weeks or like a week. So if we can kind of extract as much information as we can out of a single experiment, that's like the goal essentially. So that's what I would say is the holy grail.
So just kind of to clarify then, you're kind of just gathering this data for a potential database that the metallurgists could look at and decide versus like an actual
exactly.
material.
Yeah, exactly. That's really great. Mhm.
Well, Wyatt, thank you so much. You got any concluding statements?
Thank you all for your questions. I'm very happy that you guys were able to understand the research. I'm glad that you guys enjoyed it, and thanks for this opportunity. It was really great.